Kruskal's algorithm is one of the most widely studied and applied greedy algorithms for constructing a minimum spanning tree (MST) of a connected, undirected, weighted graph, and its appeal lies in its conceptual simplicity, efficiency, and strong theoretical foundation. The goal of a minimum spanning tree is to connect all vertices of a graph using a subset of its edges such that the total weight of those edges is minimized and no cycles are formed. Kruskal's algorithm approaches this problem by treating the graph as a collection of individual edges and progressively selecting the smallest edges that do not form cycles, ultimately ensuring that all vertices become connected in the most cost-effective way. The algorithm begins by sorting all edges in the graph by increasing weight, which is the core of its greedy strategy. At every step, the cheapest possible edge is considered first initially. Each vertex is treated as a separate component or tree. Kruskal's algorithm scans through the sorted list of edges and adds an edge to the growing forest only if it connects two different components. In other words, it must not create a cycle. When an edge is added, the two components it connects are merged into a single component. This process continues until all vertices are part of a single connected component containing exactly v-1 edges, where v is the number of vertices, forming the final MST. A crucial supporting data structure in Kruskal's algorithm is the union find or disjoint set union (DSU) structure, which efficiently keeps track of which vertices belong to which components and allows quick merging of components using operations like find and union, with path compression and union by rank optimizations. The union find data structure ensures that cycle detection and component merging can be performed almost in constant time, making the algorithm efficient even for very large graphs. The theoretical correctness of Kruskal's algorithm is grounded in two key MST properties: the cut property and the cycle property. The cut property asserts that for any partition of the graph into two disjoint sets, the minimum weight edge that crosses the cut must be part of every MST. And Kruskal's algorithm naturally respects this property by always selecting the smallest available edge that connects two different components. This ensures that each greedy choice is safe and contributes toward the optimal solution. The cycle property, which states that the heaviest edge in any cycle cannot belong to an MST, serves as justification for skipping edges that would create cycles, because adding such an edge would contradict the cycle property by introducing an unnecessary, heavier connection. Together, these properties guarantee that Kruskal's method always yields a valid and optimal MST. This combination of conceptual clarity and provable optimality has made Kruskal's algorithm a fundamental part of algorithmic education and textbook treatments of greedy strategies. In terms of computational complexity, Kruskal's algorithm runs in O(E) log E time, where E is the number of edges in the graph. The dominant factor in this complexity is sorting the edges. Once they are sorted, the union find operations on each edge are nearly constant time, because the number of edges often grows faster than the number of vertices. Especially in dense graphs, the E log E complexity is practical and efficient for many applications. Kruskal's algorithm is particularly well suited to sparse graphs, where the number of edges is relatively small compared to the maximum possible number. In such cases, sorting the edges is inexpensive and the algorithm performs extremely well, compared with Prim's algorithm, which grows a single MST from a starting vertex by repeatedly choosing the lightest edge that expands the tree. Kruskal's algorithm performs its work by stitching together many small components until they coalesce into one. This makes Kruskal's visually and conceptually appealing. Instead of seeing the MST expand outward from a root, One watches multiple fragments merge like puzzle pieces until a single, optimal structure emerges. This reassembly-like process is why Kruskal's algorithm is sometimes described as building a minimum spanning forest that gradually collapses into one connected tree. Kruskal's algorithm is used extensively in real-world applications that require efficient, cost-minimizing connectivity. For instance, in network design, Kruskal's algorithm can help compute the least cost way to connect a set of routers, servers, or communication towers using cables or wireless links, because it emphasizes selecting the cheapest possible connections globally rather than expanding incrementally from one location. It is especially useful when the structure of the graph is irregular or geographically scattered. In transportation and road network design, Kruskal's algorithm aids in determining the cheapest set of roads or pipelines needed to connect a set of cities or distribution points without redundancy. In clustering algorithms, particularly in hierarchical clustering, Kruskal's algorithm can be used to build MSTs from a graph representation of data points, where removing the highest weight edges results in natural grouping of data. In image processing, MSTs constructed via Kruskal's algorithm play a role in segmentation methods where pixels or regions are connected according to similarity weights to reveal coherent image segments. In electrical engineering and circuit design, MSTs ensure minimal wiring length, reducing material costs and improving efficiency. Additionally, in approximation algorithms for solving nitrogen monophosphide hard problems like the traveling salesman problem, TSP, Kruskal-based MST construction provides an essential foundation for bounding and approximating optimal solutions. The ability of Kruskal's algorithm to work flexibly with disconnected graphs also makes it useful for computing minimum spanning forests, which are essential in analyzing large-scale, real-world networks that may not be fully connected. One of the most powerful aspects of Kruskal's algorithm is its modularity and adaptability. Because it relies on sorting edges and performing union-find operations, it lends itself well to parallelization and distributed computation. Components of the graph can be processed independently, and edges can be sorted using parallel sorting algorithms. This makes Kruskal's algorithm highly applicable to modern computing environments involving large datasets, cloud-based computation, and massive graph analysis. Furthermore, its elegant structure has inspired numerous variations and improvements, such as algorithms that handle dynamic graphs where edges may be added or removed and the MST must be updated accordingly. Extensions like randomized Kruskal algorithms and hybrid approaches that combine Kruskal's and Borufka's ideas allow even faster MST construction for massive graphs. Despite its apparent simplicity, Kruskal's algorithm conveys deep lessons about greedy strategies and how local choices, if made correctly, can lead to globally optimal solutions. Its reliance on fundamental graph properties, combined with practical efficiency and a clear conceptual flow, makes it a timeless algorithm in computer science. Whether constructing efficient networks, analyzing data, powering image processing techniques, or forming the backbone of more complex optimization systems, Kruskal's algorithm remains an essential tool. Its popularity in textbooks, classrooms, and real-world applications attests to its enduring value. A powerful blend of elegance, optimality, and practical utility that continues to shape the field of graph algorithms.